Okay, I want to go over how to do the area problems. We had talked about in class how basically you need to know a couple formulas to do the area problems. Number one, you need to know the area of a rectangle, which is going to be length times width. And then you also probably are going to come across the area of a square, which is going to be S stands for side squared. And the reason why they distinguish those two formulas is remember that a rectangle has two different dimensions and a square has the same dimension on all four sides. So we talked about two key things to do well on these kinds of word problems. They're the same thing as we did with emotion. Number one, you're going to want to draw a diagram. And it's really going to be important with the diagram to help you figure out how to write your equation. And the other is to use a chart, because you've got at least two different objects with two different sets of dimensions, so you got to keep things straight. Okay. And in all of these kinds of problems, you're going to see something that looks a little bit like this, where you're going to have either some sort of beginning rectangle, and then you're going to increase the length and or the width so that you create an additional amount. And remember, area is simply the looking inside the shape, not around the edge. That's perimeter. And so basically when you've done this picture, you've formed two rectangles. You formed the black original rectangle, and then you've formed the outer rectangle that extends the black to the green. And to make up the difference between the little rectangle and the big rectangle is that additional increase in area. So in general, a formula that we would use for a picture like this would be the area of the original, and I'm going to just say rectangle for our purposes, plus the area of the increased amount. So let me go back and kind of color code these. And the area of the increased amount is going to be that kind of L-shaped that's filled in with red. And that's going to equal to the area of the large or outside rectangle. So that's going to look like this. Oops, actually, let me clean that up a little bit. That actually goes down a little lower. Like that. So that's pretty much how half of them will work, and let me show you on the next screen. The next half will be more like you have a rectangle that is completely surrounded. Could be by a walk path, it could be by a frame of a picture, and that the dimensions from each of these sides, from the original to the outer, is going to be the same amount of value, okay? And sometimes they'll tell you it, and sometimes you have to figure it out. And again, when we do this, we create additional area. So when I'm writing the equation for something like this, I get the area of the original, and again, we're going to just use rectangle, could be square. Oh, there I go. Saying rectangle and writing square. And so for us, that's again the black guy. And then we're going to add to that the area of the increased amount. So this is the one. This is kind of the weird picture. All we're focusing in on is the red portion. And that's going to be equal to the area of the outer rectangle, which in this drawing would just be the large green one. Okay? So let's go ahead and look at our first picture, our first problem, excuse me. And we've got the directions are going to just tell us, are just going to tell us to solve. Oh my goodness, sorry. And it says the length of a page of a book is 2 centimeters greater than the width of the page. A book designer finds that if the length is increased by 2 centimeters, and the width is increased by 1 centimeter, the area of the page is increased by 19 squared centimeters. What are the dimensions of the original page? Okay, so we're going to start by drawing a picture of our original page. And I know to draw a rectangle because I'm familiar with reading enough books that they are rectangular in shape most of the time. And what I want to do is look in that first sentence, because they talk about both dimensions, and I want to look to see who they mention last. They say the length of a page of a book is 2 centimeters greater than the width. So because of that, I'm going to let the width be x. The length of the page is going to be 2 centimeters greater than, so that's going to be the original width, and then we're going to add 2 to it. Okay. Now, it says a book designer finds that if the length is increased by 2 centimeters and the width is increased by 1 centimeter, then the area is increased by, so this portion here, that little L shape, 19 squared centimeters. Okay, so let's get into our chart. We're going to call the original page, if you call original rectangle, that's fine too. And then we're going to call it the increased page, or the new page, or the larger page, however you want to. And then the top is always going to be the same, and we're going to kind of transform the formula. Instead of doing it traditionally with A equals LW, we're going to say LW A. And remember what we're going to do mathematically. We're going to multiply the length times the width. The product is what we're going to write into the A column. And it's the A column we're going to use to do our stuff. So the original page had a width of 2 and a length of x plus 2. So the area that we're going to be using is their product x times the quantity x plus 2. Okay, now when it comes to the new length, we still have the x plus 2 from the original length, but now we're going to add on 2 more centimeters for a grand total of x plus 4. Okay, and then on the width, we had the original x, and then we're going to add on 1 more. So that's your new, I'll write it out again in black. That would be your new width. So the area would be length times width, width times length. Commutative property says it doesn't matter. So if you take a moment, let's just go back screens. Our problem here looks like this picture. We're just increasing the length on one side, the width on the other side. We are not going all the way around it. So we're going to take the area of the original rectangle plus the area of the increased amount, that kind of L-shaped piece, and that's going to be the area of the large or outside rectangle. So that's the black through the green. Okay? So that's what our formula is going to be. Oops. Over here. So we're going to have, I'm going to write it down here, area of the original plus area of the increased amount equals area of the new. Just say it that way. So for us, the area of the original page is the x times the x plus 2 plus the area of the increase. That's where this 19 comes in. Equals the area of the new guy. So we just start distributing and foiling and matrixing and whatever else way we want to do a double distribution. We get x squared plus 2x plus 19 equals x squared plus 4x plus x plus 4. On the right side, I'm going to combine up like terms. I get x squared plus 5x. So at first I'm a little bit nervous because I have x squareds, but as soon as, actually let me do this in color. As soon as I try to get the x squareds together, notice that they are going to cancel out. So what I'm going to do is go ahead and get all the x's on the left by subtracting 5x from both sides. I'm going to get all the constants on the right by subtracting 19 from both sides. And we get negative 3x equals negative 15. And so our final step would be to divide both sides by negative 3. And we get x equals 5. So remember what our question is, or what are the dimensions of the original page. So this, hold on a second, I think I have an extra mark here that I shouldn't have. There we go, it just equals 5. So what we're going to do is we're going to take this answer. So we've got the inner picture, which is the x plus 2 area. We're going to add the increased amount, which in our case is the area of the frame. And that's going to be equal to the outer. So we go ahead and multiply, distribute. We get x squared plus 2x plus 168 equals x squared plus 6x plus 8x plus 48. Combine up like terms on the right. And just to let you know, we tend not to be super mean. So we tend to get whole number answers, maybe fractions like a half. But if you're getting a negative, you know you've done something wrong. So we're going to subtract x squared from both sides, which blissfully cancels them out. We're going to get into our next chapter in which they will not cancel out, and we're going to have to teach you a new strategy in how to solve that. So at this point, I'm going to go ahead and get my x's on the left by subtracting 14x from both sides, and I'm going to go ahead and subtract 168 from both sides to get my constants on the right. And we end up with negative 12x equals negative 120. When I divide both sides by negative 12, I get x equals 10. Now again, we're asked for the dimensions of the picture, which means we're going to take that answer and go back to the original dimensions, and that's how we're going to come up with our answer. Because we have two answers, we're going to have to label which one's which. X represents width. I don't use variables. I say width equals 10 and then look for a label. Again, we go to centimeters. Now for the length, I'm going to have to add 2. So 10 plus 2 is 12 centimeters. Okay, and I've got one more for us to try. And this one talks about a swimming pool. A rectangular swimming pool is 4 meters longer than it is wide. If a sidewalk (2 meters wide) is placed around the pool, the area covered by the pool and sidewalk is 192 square meters. Oh, sorry, I'm not done yet. The area covered by the pool and sidewalk is 192 square meters greater than the area covered by the pool alone. Find the dimensions of the pool. Okay, so let's draw a picture of this. And it's kind of like the last one. I'm going to just change up the picture a little bit. And there's our swimming pool. And again, I read that first sentence, trying to figure out who's mentioned last. And it says, rectangular swimming pool is 4 meters longer than it is wide. So width is going to be our x. And the length is going to be longer than. So that means we're going to add the 4. Now, this one has a sidewalk that's put all the way around the pool. And so all the way around on all 4 sides. And it told us that it is 2 centimeters wide all the way around. Okay. And the last thing it tells us is that this area is going to be 192 squared centimeters. Now, when we do our chart, we've got pool, so pool and then pool with sidewalk. Sorry if you guys can hear the gardeners are here today. So if you just take a quick gander, I'm going to go back one slide, and you can see how this picture looks very similar to the last picture. Okay, so the pool has the dimensions of a width of x and a length of x plus 4. And then when I'm looking at the width, with the sidewalk, so I have to go from the orange to the black and then the black to the orange, I'm going to be adding on 2, oops, sorry, and 2 to get all the way around for a grand total of x plus 8. 4 plus 2 is 6 plus 2 is 8. And on the other, the width, I will be adding the 2 dimensions, the 2 additions to it for a grand total of x plus 4. So the area of the pool itself is just x times the quantity x plus 4. And for the pool with the sidewalk, it's x plus 8, x plus 4. Okay? Now, this one you can either just do it the same way we've been doing it, and just say the area of the pool plus the area of the increased amount, which in our case would be the sidewalk, would be equal to the area of the outer rectangle, which would be the area with the pool and the sidewalk. Now, if you want, and I'm going to give you this alternative, is you can actually translate it literally. It says the area covered by the pool and sidewalk, so that's the x plus 8 times x plus 4 is equals 192 square centimeters, 192 square centimeters greater than, so the switcher phrase, the area covered by the pool alone. So if you notice, it's the same strategy that we talked about before, but this one puts the big rectangle's area on the left as opposed to right. Doesn't matter at all. Alright, so let's do the math. So we get x squared plus 4x plus 8x plus 32 equals x squared plus 4x plus 192. Combining up like terms on the left, we get x squared plus 12x plus 32 equals x squared plus 4x plus 192. And again, when we start doing opposite operations and we try to get the x squareds alone, they blissfully cancel out. So then we're going to get the x's on the left by subtracting 4x from both sides. We're going to get the constants together on the right by subtracting 32 from both sides. That gives me 8x equals 160, and then when I divide both sides by 8, I get x equals 20. So again, I'm going to take that answer, and it wants to know the dimensions of the pool. So we're going to go back to that part of my chart. I have 2 answers, so I'm going to label them separately. The width was the x value, which is 20, and this time it's meters. It's super important that you guys end up getting the correct labels. When you don't, it doesn't make sense. Like if you put centimeters, that would be like a pool for a mouse. Okay, and then to get the length, 20 plus 4 is 24 meters. And so those are the dimensions there. All right, have fun with this.